Like let's suppose the accuracy with infinite amount of samples is like really nice. But then with the amount of samples you're taking, you're already in a very satisfactory bracket. And again, let's consider the case where accumulating samples is an expensive task. Would it really matter spending a lot more to just get 0.2% of accuracy? If that is important in your use case, then go ahead. But if it's not, then don't spend the money accumulating more samples when you're already like performing good enough. So that's the main takeaway that I want you guys to take away from here, from this slide, is that based on the class separation and the amount of samples you have, you can actually see what's the accuracy going to be, and whether you really need to collect more samples to go into a higher bracket of accuracy or not. But that's the decision that we leave entirely to the user to make that decision. Now that we know that we can do a lot with the data set, even before we start building the classifier. We know what's the minimum achievable error that we can get, what's the geometry of the decision boundary that we can get, and thirdly, how many more samples, or with the given sample size, how much accuracy I can get. And again, like if I need more samples to achieve to go into a higher accuracy spec. Now that you've done all of that, you can go about choosing your classifier, and it falls within the minimum achievable error. All really nice. And now you're satisfied with the qualification part of it. You've chosen, you've done everything in the pre-development, you've done everything in the qualification stage, and you've chosen this amazing classifier that performs well on training data. Now it's time that your boss or manager says, hey, let's deploy this. Let's see how this does in the real world. Now, what do we need to do to keep a check on this model that is in the real world? And this is where I come up with, this is where we say that data drift is important. Like, obviously the data that you observe in training and testing is not the same. It can drift, it can change. And that's where it's important to track the shift of this. Because a simple example can be that, let's suppose that you have two infrared sensors that are giving you some feature values. And on the first 6 days, it's been spitting out, you have two infrared sensors from the same company that designed XYZ, and they're spitting out some values that you're sensing the neighbor and environment and everything. But on the 7th day, on the first 6 days, you have the first one. On the 7th day, let's suppose one of them goes back, and then you replace it with a different company's sensor. Now, obviously, there might be some discrepancy between, like, the values might not be the same. You might have to recalibrate or something. But there's a change that has occurred, which might be minor, but it's important to check the repeatability of your feature values as well. And this can play a huge role in like tracking in your model monitoring. And so another thing is that using the same divergence metric that we have, that we used to measure the class overlap, we can apply this to the difference between the source data. That is, when I say the source data, it is the data that your model was evaluated on, trained, evaluated, and then the target is the deployment. And so based on that, we have a loose, no need to go in all of this. All we're just trying to say over here is that the error or the error shift from the source can be approximated this way, which is the difference between the source and the target. Now, how do we use this? That's when your model is deployed, you can use our class overlap metric or the divergence metric. I'm using those two terms interchangeably. You can use that to track your error in deployment, and then you as a user can set a threshold that, hey, when the error sees a certain limit, maybe throw me a message or maybe throw me a notification or something, which can imply that retraining needs to be done, or I need to look at the data because a significant shift has happened. Now, one of the ways that shift occurs is through your own features. Like I said, you might be using sensors from two same companies for most of the time, and then on the seventh day or whatever, that you have to replace it with a different company sensor, and then in that sense, like the data has shifted, the way that you're getting it has shifted. You might think that it might be the same, but let's suppose that the data or the feature value that you're getting has changed a little bit. Now it's important to track that. And so based on, so these are the feature metrics that our API provides, which are feature level shifts. So we track each feature and how their distribution is changing based on the insight to each day or however frequent your samples are coming. Now, the second thing is repeatability, because you want your data to be repeatable. Like if I'm sensing the same environment today, and if I'm sensing the same environment tomorrow, I want to know whether the values are the same. And so we borrow some metrics from measurement theory to gauge the repeatability of our features. Now, secondly, lastly, we have feature separability, which is given, it essentially says that how important my feature is to this data set. And what this measures essentially is how well my feature can separate my current data set, just that feature. And an amalgamation of all of these gives us a feature ranking as to what each feature is ranked at. So obviously the highest ranked features will have low feature covariance shift. They won't shift much. They will have high repeatability, and they will have high feature separability as well. And so, those are the feature metrics that our toolkit will provide. Essentially, I'm saying the same thing, that what's the takeaway from data-driven metrics from our API is that measuring the amount of drift that has undergone from source to the target, from training to post-deployment. And if so, how much impact has happened, which is the error in deployment curve that we're tracking, and if a retraining event needs to happen. And then thirdly, we want to know which features have shifted or whose distribution has shifted the most. That way, either we can drop that feature or maybe re-engineer another one, and which might take its place. And lastly, we have some model metrics, which are again, these are widely known. The first one is the performance that we are saying that when in deployment you're getting the data is when in deployment you're getting data as well. You still have an ability to track how much error that you can achieve based on what we've done before. And so you can compare what your model is performing now compared to that baseline. And secondly, a lot of times models need to be calibrated as well. And so Bright Score is another concept that helps us keep model calibration intact. And then thirdly, we always test sensitivity to different weights of your model. Like your neural network have different weights. Like each layer has different nodes, and each of them have weights. So it's important to check which ones are more sensitive and probably fix that. And one of the main important thing is detecting data drift, which we've discussed. And at the end, we just like to say that this is still a work in progress. We're still building this to scale up. And by no means these metrics, the feature metrics, the model metrics, and the dataset metrics are comprehensive in totality, because the variation in machine learning applications is so wide that a metric to you might not be as valuable to you. And so this is an ongoing task of like trying to grow Bain to cater to different market segments. So far, we've gained some traction in the defense sector, and we're working with Raytheon to build this API, and hopefully we move on to other market segments like healthcare, where in terms of like drug discovery or patient plan recommendation, that sort of stuff, and yeah, and again, we're like always open to discuss more how we can grow data, how we can how can incorporate more metrics that are useful and will help machine learning algorithm designers behave in a more intuitive, like have a more intuitive insight into their data set rather than just going ahead and looking at it. So if you have any questions, feel free to ask.
I have a question.
Yeah.
When your toolkit's available, where can we find it or more information about it?
So right now we don't have a data set. So we don't have it's a private repo right now. So we've not gotten that far yet as to making it publicly available. But yeah, but if eventually, yeah, we'll probably let you know.
That's it. Thank you.
Yeah. And any other questions? Yeah.
Are you guys open to applying the data models and the analysis on different data sets, or just to compare it to different types of markets and different types of level of data?
Exactly, yeah. So we just don't want to limit ourselves to just not only just the market segments, but also to the data sets. Like I know this one, I specifically discussed classification, but that's not usually the case. Sometimes you want object detection, object tracking, and all those other things. And so yeah, we don't want to limit ourselves to just one particular. And also I know that there are a lot of other machine learning ops tools out there which do model tracking and data detection. Like Arise is a big name out there right now, and they promote their API aggressively as well with different conferences and everything. And but one thing that we want to do a little bit differently is taking a step back and sort of analyzing the data at a more, so we are more we definitely want to be more theoretically rooted and more intuitive about the way. Essentially, what we want to be is like GitHub pilot, maybe, or like an ML co-pilot, where instead of it writing code for you, it's more like, hey, I'm your buddy, I'm like your sounding board. Like, hey, I have this data set, what can I do with it? I want to exploit the data set first and see what it can give me before I even jump in. And yeah.
First off, I think it's a amazing toolkit if you can use it. Second question is, what would, just as you said, what would the interface be? Or it is API or Python API that we use in our code, or it's?
So it's going to be a Python API. So because what we're doing is we are covering a lot of breadth, from data acquisition to model qualification to model deployment. We want it to be easy as a plugin that goes into your ML pipeline. And that way, if you are interested in just a certain section of metrics or measures that you want to use, then you can avail that. But if you want to use it completely, it can plug in at different segments in your, because I understand like the way machine learning teams work usually is like the data scientists are a little different, the algorithm designs are different, and the testers are again different. This might not be the same everywhere, but when we took part in the regional I4 challenge, and then some of the things that we uncovered was like it's a little bit separated, and so to cater each of their needs, we wanted to be separable as well, and sort of like maybe make use of this part of it if you so choose to like, which might be a little harder to sell because it's collaboration between different teams then.
And I assume it works with multi-label classification.
Yes, exactly, yeah, so this, the separation that I just showed, it can be easily extended to multi-label classifications, yeah.
And also the example we raised is actually like highly dimensional.
Yeah,
What, next question is, what will it scale up if you have, image classification, which.
Yeah. So I wanted to put some of the stuff out, but like my co-PIs were like, it might be too technical or it might be just too deep. So I was like, I'll hover on the top. But so far we've not seen any issues with image data sets. Like we've worked with the but what our initial testing has been on like these MNIST and CPAR data sets where we've just chosen two of their classes and we've performed like class separation or just geometry detection. But again, like when it comes to like geometry detection, it becomes a little bit more complex because like I said, simple figures like this, you can have their very numbers and be like, hey, this is easy. I can figure out what this is. But as the geometry becomes more and more complex, all you can see is like how many holes are there, how many voids are there in your data set, and then that's about like, yeah. So essentially, like maybe it so to an abstract topologist or something like that, it might be easier to figure out, but we're still kind of like on simpler data sets, it makes sense to have this geometry decision on. But on complex data sets, it might become hard to interpret what exactly is your joint. Yeah. And yeah, so one of so this I'll just discuss the motivation for this. It was just mainly because we just saw a lot of pain points, different like how do you what happens to a lot of machine learning models after deployment, and which came to our one of the things that we definitely want to incorporate in DAME is this scenario where now you have your machine learning model in deployment, and you have tons of data in deployment, but there's a very costly human annotator in between where it takes days. Maybe it's a lab tech or someone, and he takes 7 days to annotate your data. How would you still go about measuring your model's performance when you have a 7-day delay? And you might have a time crunch. You want to know if my model is drifting or if it's not performing well. I don't have 7 days to wait. And so that is another pain point, or that's another feature that we want to add to our toolkit, that in a data or like a label star regime, we still want to do well, or we still want to estimate the accuracy really well. And so if you guys have any ideas about it, or you've been thinking about it or something, we're more than happy to like talk and yeah. I think I finished.